So good morning, everyone. Is it audible? So I'm Mathew from Tata Consultancy Services, and I'll be presenting my experience with optimizing AMBER, which is a molecular dynamics application. So this is the flow. I'll be going over the background of AMBER, how the original implementation was, and what changes we made to it, and the main hotspots, and the two main hotspots I'll cover in little more detail: the Born Radii computation and off diagonal, and then the cache blocking implementation. So okay, what does AMBER stand for? AMBER is a molecular dynamics software for most HPC. Those who are in HPC will call it an n-body simulation. It uses computational technique to model motion of group of particles. It can be atoms or molecules, and there are many fields that are using molecular dynamics nowadays, including material science, drug discovery of viruses, protein simulation. One such example, even in material science, is they use it for battery simulation. Samsung is an example, not a good example, but they use AMBER for battery simulation. So how does the flow? So if you see, it's how is the flow of the simulation? There's a simulation setup that it reads a file. So you have all the molecules or atoms which are arranged in a 3D space. So that's all input from a file. You read the file, and there is a simulation setup which you can. So original implementation in MPI, so you can scale across multiple nodes, and main calculations are these: Born radii calculations, off diagonal energy calculation, diagonal energy calculation. Then there is the non-bond energy calculations. There is all the bonded energy calculations. And so when you calculate all the energies, the next step is to then derive the force from it. Once you have the force, you derive the velocity. And when you have the velocity, you can now know how each atom is going to move. So you update the position, and normally this time interval for which you change the position is in picoseconds, and you upgrade to the next time and repeat the simulation. If you do this a number of times, you know how each atom is going to move. So this is so typically the performance of the molecular dynamics package is measured in the nanoseconds per day. That is, if you run the simulation for a whole day, how much nanoseconds are you going to simulate? So when we did profiling using ITAC and VTune, this is what we found for KNC. So we started with implementation is on a KNC. The MPI overhead was about 18%, and this calculation was taking 65% of the time, and a rest divided among diagonal energy and Born radii calculations. So you could see that MPI, so if you are running it on a KNC which has 61 cores, you would probably use 60 or 120 MPI ranks to simulate, and there was a big overhead of MPI. So if you see these three hotspots which I have mentioned, we have all the three hotspots have very similar flow. You could see you take a neighbor, take a atom, find its neighbor, and you compute, get a lot of data about it, of the atom and its pair, and you collect this data and do maths operations. So it has a lot of exponential, inverse square root operations happening. So to speed it up, what it does is, for all the neighbors, you collect this data do these inverse square root or exponential operation in a SIMD manner, and then you go to the actual compute loop. Because these compute loops are not vectorized, this step actually speeds up the computation, so that all the maths operations are. So this is the original flow, and if you compare radii or off diagonal or diagonal energy, the flow is almost the same. You have a neighbor, collect the neighbors, you gather data for maths operation, you have the actual mathematical operations which are high CPU consuming ones in a SIMD manner, and then you calculate. So what going in detail, how is it the work divided among different ranks? So if you have 60 ranks, rank 1 will take atom 1, and rank 2 will say atom 2, and it will go up to 60, and again rank 1 after finishing atom 1 will go to the 61st atom and process for it. So this is how the original implementation was, and to save on some computations, what the original implementation did was, it is a triangular loop. So you have an outer loop going from I1 to the number of atoms, and the inner loop goes from I plus 1 to atom count. So J is from I plus 1. How it saves you on half the number of makes the loop from n square to n square by 2, but there is a cost. Now you are having to do a reduction, some information about since you are computing J's impact on I, you are also computing atom I's impact on J. So this makes the loop so each rank has partial information, and you have to do a reduction to get the final data. So this is how the original looping structure was, and what we did was, now to make this vectorized. So we calculate radii, which was not a vectorized loop. We made a lot of changes, made it vectorized, and we did away with these 3 loops and made it into a single loop. So we had a single vectorized loop instead of 3. Now what next we did was, for cache blocking, was this. We took we gave each thread. So now the implementation is MPI plus OpenMP. So each thread now gets 8 I atoms, and then it iterates through about 128 J's to get the neighbors, and then once it processes 128 J's, it goes back to the first atom. So this way we did a cache blocking for radii computation. So we did experiments with how many atoms should be involved in the cache blocking, starting from 8, 16, 32, and we finally found that 128 is the optimal amount for this kind of loops, and this is how we did a cache blocking for radii. So other major change is we removed the triangular loop. So we made it a squared loop again. So this eliminated the need for reduction. Now in this case, we found that straight away removing reduction straight away gave us a gain of 50% of time for this for radii. So there is no need for any thread to communicate, or there is no need for reduction. So removal of reduction gave you a very good advantage. So this is for radii. Next is the main culprit, you can say the off diagonal energy, which was taking almost 65% of the time. So here again we did away with the neighbors, and we, instead of computing the neighbors, we did it for all atoms, all atom combinations. Now why did it help here? Is it helped to normally what we see is the cutoff for off diagonal energy computation is quite high. So if radii impact radii computation, you see that the cutoff is low, so about 20 to 30 microns. So very few atoms come up as the neighbors. But when you do off diagonal, the cutoffs are usually in the 40 or 50 microns range, and you will see that a lot of so you don't really get an advantage of using the neighbor list. So here again, just converting this loop also to OpenMP hybrid implementation, OpenMP plus MPI, removal of the neighbor list, and it gave us a very good advantage. Next is, why don't we try to remove the reduction? However, this loop behaved very differently as compared to radii. As soon as we made this triangular loop into a squared loop, the time simply doubled. So the removal of reduction had almost no impact on the time taken. So we had to keep it a triangular loop. So when we have MPI, how do we now distribute a triangular loop to different MPI ranks and the threads? So we had this arrangement where we find the area under the triangle and give equal amount of work to each rank, and this is how we did. Rank 1 will have a lot less number of I items, but the area under each of the section, if there are 4 ranks, would be like this. Now other thing we did along with this was implement the automatic balancing. So when we have disparate, since we are working on KNC, we could also now use host plus KNC using MPI. So if you are host, you can run 2 or 4 ranks and 1 rank on the KNC. We could use the automatic balancer. So it will, you don't have to give any further detail. You initially starts with giving each rank equal work. Every 10 seconds it monitors how much is the time taken by for each of the rank for processing. Whichever is slowing down, we give it more work, and so it balances every 10 seconds, which is a configurable item. So by doing this, we could actually scale across disparate servers. It could be two CPU server with a 4 CPU server. It could be a CPU plus a server with a KNC. So this is next. We again did cache blocking. So we go. So if this is rank 4, again 8 threads. 1 thread gets 8 ranks, 8 atoms, contiguous atoms, and it goes through J's and then comes back to the first atom, which is processed. So this is also for the initial part. It requires a peel loop, but rest is all a square. So this gave us about 5 to 10% advantage improvement. So starting with 0.09 nanoseconds per day, we were able to go up to 0.49 on the KNC. Not just through cache blocking, there were a lot of, so main changes were the hybrid implementation, OpenMP plus MPI, but there were also a lot of other changes done. These changes are covered in this paper, and which is in 2014. Once we had done all these changes on KNC, we did something which gave us a real big boost, that is moved to a KNL. So from 0.49 it straight away jumped to 0.91. So the decision to keep OpenMP plus MPI implementation was proved very helpful here, because when we moved here, we already had an implementation which works very well on KNL. We put it in quadrant mode. We use 4 ranks per for a one KNL, 1 per quadrant, and then the number of threads were equal to the number of cores using the on each quadrant. So this really gave us a very good advantage of, because initially we struggled a lot during when we were working on KNC to do an offload. So then that time at least the Amber community would not have accepted the offload code. That's where we decided to go for a MPI plus OpenMP implementation, and that proved really fruitful when KNL came out. So now how do we modify this loop? So when we came here, giving data which atom, so you will see here balancing was a bit tough. So if one thread gets this set of atoms, it had a lot of work to do, and when other thread would be taking this set of atoms, it has less atoms. So you had to have a dynamic balancing when we had this kind of a structure. So we wanted to get a better solution. So there we went to an alternate tiling approach. So here, instead of processing at this side, we just shifted that to the other side. We took the mirror image instead of and took alternate tiles, and this straight away gave us a very good reduction, 14% reduction in the timing. So it was easy to distribute now the work to each thread. You find how many tiles you have, and now distribute work to each tile. So this advantage is it still did not make the loop. The loop remained n square plus 2, and it is not n square, and it is easy to distribute ranks. Okay, then when we actually scaled, so we got very good results with one nucleosome benchmark, which is about 25,000 atoms. When we increase it to 100,000 or 200,000 atoms, we found that it is performing really poorly. So what happened is, when we increase the number of atoms and we keep a small tile size, the number of tiles is really huge. So we had to have a balance. So it doesn't, one tile size would not be fitting for all workload sizes. So we had to come up with a equation to find what is the optimal one. So this is how so though for the 25,000 atoms it was working well, as soon as you increase it, just sheer number of tiles was creating a problem. And what we did is, now for different workloads we experiment with different tile sizes. So and then for 25,000, for 75,000, 150,000, we found the optimal tile size, and then plotted a graph, and then we used that equation to now find the. So even though it is ideally tiles should have a size which everything fits into the L2 cache, but for larger workloads it does not work that way. So it is not strictly a cache blocking implementation when you are increasing the number of when the number of atoms increase beyond 100,000. So when we started out on KNL, these were the time taken in milliseconds for each of the loops. Radii used to take 36 milliseconds, off diagonal 95, diagonal used to take 30. And finally, when we moved to the 7250, these are the current times. Radii time takes 24 milliseconds, off diagonal 72, diagonal 18. So we have now reached 1.36 nanoseconds per day performance. So starting from 0.09 on KNC, and on KNL we have reached to 1.36. So results, if you see compared with Broadwell EP, which has this configuration of 2 sockets, 18 cores per socket. KNL is 1.6 times. If you compare with NVIDIA K80 card, the computing is we have 12% better. But there is a catch to this. When we see NVIDIA cards, double precision performance, we are better. But when we go to single precision, NVIDIA has one advantage, that the single precision performance is 4 times that of double precision. So while Intel only gives 2x. So there is a drawback. So when you say computing, it is for double precision, not for a single precision. We did experiment with other modes. So MCD only gives 2.4 times DDR performance, and flat mode is about 9% better than a cache mode. So yeah, so that's the this is the last slide. So we started with 3 hotspot having very similar flow, but optimizations that worked were really different for each. Clearly there are other considerations. So what one worked well with when you squared the loop and remove the reduction. Other loop we had to keep the reduction. Squaring just doubled the performance. So there are other consideration: amount of computation, amount of data, the conditional statement in each. So is there an alternative? I mean, do we have to experiment with all these combinations to find are there indicators in VTune which determine any modeling? So these are maybe the discussion points. So that's it from me. I think there is some session from in the afternoon which may help. It talks of some modeling techniques, but yeah, this is end of. So any questions?
Thank you.